I guess really there is no more new material to go over before we get to the exam. The exam will be, like I said last class, 10 multiple choice questions and 2 long answer problems. You should not be surprised if both of those long answer problems are first law type problems. Problems like the one that we were doing yesterday, right? And there's only so many different levers that we can pull, right? We can change, like a PV relationship, so you calculate work differently. If it's water, we can, have things happening in different phases, so you're interpolating differently, so that you're demonstrating that you know how to find subcooled liquid, specific internal energies. Or we can make it an ideal gas, which is what we're going to do this class. Now, with ideal gases, we also have 2 different paths we can go by. We can either take constant specific heat, right? CV times delta T. We can make the right assumptions for that. Or we can do variable specific heat and look values up in the tables. And today, I hope to be able to do both. But before I do that, I just want to kind of go through a bit of the flow chart of how to work these kind of problems, right? So there's 2 different ways that we'll kind of go through this. And I think that this is helpful because sometimes I think right when you start an exam, right, or an exam problem, you look at the problem and there's kind of that moment where you're like, oh, I'm not really sure what it is I'm supposed to do, right? And I think that the value that one of the things that we're trying to learn in this class is this systematic approach. So even if you feel totally lost, there's some things you can start to do, right? To kind of build up that inertia, right? To get the ball rolling. And then as you do that, then hopefully you'll be able to, eventually find out where you're going with the rest of the problem, right? We saw last class that drawing PV and TV diagrams can be helpful. One, if you're drawing a PV diagram, it's helpful because it'll give you an idea of how to find the work, right? Because you know that work is going to be the area under your curve on that PV diagram, right? But it also is helpful if you're dealing with something like water because it can help you figure out which state you're going to be in for each case. Or like last class, even if you couldn't figure out whether you're, say, 2-phase or superheated vapor like last class, it at least gives you the right question to ask, right? We started to do that last class, and then we saw, well, the break point between being 2-phase or superheated was we had to see if that specific volume was above the saturated vapor specific volume, right? And once we did that, then we could fix the state. Another thing you might be able to do, although this could be, sometimes we provide this, sometimes we don't, right? But another useful thing that you can do here is to draw a state table, right? Now, state tables are nice, first because they're just a place to account for where your information is, right? So it's easy to look back, right? I would say if it's a metric problem, right, and you're writing down the pressure, I would convert it automatically to kilopascals, right? But the other thing that's nice about a state table is that it lets you see very clearly which states you have 2 independent intensive properties for, right? So that'll be kind of your starting point, right? And then you'll have to figure out if you only have 2 independent intensive properties for one state, then you can try to figure out how to move between that state and some other state to find a second intensive property. One thing you can do, I find that I don't really do this too much. One of the professors who taught this class before me was also big on making process tables. So these are process tables that, one column would be where does the process start, the next column, where does the process end, and then what's the work and what's the heat. So that's basically just trying to account for the information that's on the right-hand side of the equation there. Now, if you look at your state table, you want to start potentially, if you're trying to fix states, with where you have 2 independent intensive properties, right? So you look, if you have, say, temperature and specific volume, you know that you can fix that state for sure. If you have temperature and pressure, maybe not. You're not sure yet, right? Because it depends. If that's under the vapor dome, then you can't fix the state, right? But if you look at your state table, there might be some clues on where to start fixing states. The other thing we have to do on the right-hand side of the equation, we have to think about what's the relationship between pressure and volume? Now, often, but not always, this will be PV to the N is equal to some constant. So then you isolate for pressure. So pressure would be, so that constant C times V to the negative N. And then you can integrate from V1 to V2 or V2 to V3, depends what your states are, and find the work. So now, and this kind of all comes out from the first law, right? You use the first law to find heat, right? Because if you can fix your states, right? You fix one state, but then you keep going through, right? And then if you can find your work, then you know that delta E is equal to Q minus W. But if you've made some assumptions, maybe that delta E simplifies to delta U. And if you can find delta U and you can find work, then you can find the heat transfer, right? Now, if there's more than one process, like there was on the example that we were doing yesterday, then you basically just kind of repeat steps 4 to 7. Fix some states, find the work, fix some states, find the work, and you just add those things up to find the total work and the total heat transfer. Right? The other thing that you want to do is you want to then be able to look back, right? You want to do that that guess into the sense making thing at the end. You want to say like, are my units right? Right? Whenever you're doing calculations, when you start to put numbers in, also put the units in, right? We'll see that in today's example, that the units get important, right? And the other thing you want to do is you want to think about the signs, right? We know hip to win, so heat in is positive and work in is negative. So does the sign of the heat and or the work, does it match what your understanding is of the process? Now, sometimes we won't know what the sign should be, but like in the example we did last class, it talked about how heat was added to the system in both processes we looked at. So in that case, we expected heat to be in both processes. So we were expecting positive values for heat. Now, if a system expands, we expect that the system is doing work on the surroundings, right? So that's work out. We know work in is negative, so work out must be positive, right? Conversely, if a piston is pushing in on a system, right? If that gas is being compressed, then that is work in, which we expect to be negative. So the volume change should tell you something about the sign of the work. Okay, so here's another way to think about it, right? Because this is like a 7-step process, right? And it's kind of more like the 10,000 foot view, right? But this is actually how I'm going to go and do the problems, right? So the first question that I ask, right, is the system open or closed, right? And the good news for this exam will be that you know the answer going in. We have no open systems yet. That'll be on the second exam, right? So the system is closed, right? So at this point, all we know is closed systems. That means, right, only after I've made this assumption can I write down that delta E is equal to Q minus W, because this is the version of the first law that we used for closed systems. Now, I look at this part of the problem, and then I start to make assumptions, right? And the assumptions that I'll often make first, not always, because maybe I'm told something about potential or kinetic energy, but here I'm told, or at least in some problems, it might be reasonable to assume, that kinetic and potential energy changes can be neglected. If that's true, then the change in the total energy in the system can be approximated by the changes in the internal energy of the system, or the mass times the specific internal energy change. The next thing that I want to do is I want to look through the problem and see if it tells me what the pressure-volume relationship is. Sometimes it'll explicitly say PV to the 1.5 is equal to a constant, right? But sometimes it'll say, oh, the pressure is constant. Or you remember the one where the system expanded until the piston hit the stops, right? And then it didn't specifically tell us that the volume was constant after that, right? We had to kind of think about the problem and see like, oh, well, once it hits the stops, it can't expand anymore, so the volume stays constant. So sometimes this will be explicitly stated, but sometimes we might have to think about it a little bit to try to figure out what's going on. right? And then what we do is this work term, it becomes the integral of P dV. So if we can cast the pressure as a function of volume, right? This V with a line through it, I didn't go through all my notes. This is just another way of writing volume. So then if we remember how to do integration, then we can integrate this and get an expression for the work, right? Now, I figured out what I can on the right-hand side. I haven't taken heat transfer class yet, so I can't figure out heat directly. I'm going to use the first law to find heat unless it's given to me, right? So now the left-hand side of my equation has gone from being the change in the internal energy to being the mass times the change in the specific internal energy. And I got to ask myself, what's the fluid, right? Now, this is always a two-part question, right? So if it's what's the fluid and it's water, then I got to ask myself, is it a subcooled liquid? Is it a two-phase mixture? Or is it a superheated vapor? But if the answer to the question is what's the fluid, and the answer is, oh, it's an ideal gas, then I got to ask myself, well, am I supposed to model this as constant specific heat or variable specific heat, right? And on the exam, I will tell you which way to go, right? Now, the best thing to do for you is to do it the way that I ask you to do it. But if you feel like you don't know how to do that, the next best thing to do is to do it the other way, right? The worst thing to do is leave it blank, right? So you do everything you can to avoid leaving something blank, which is kind of the point of writing down this process flow. Because, like I said, for me, it's always heartbreaking when I get an exam back and it's blank. Because I think an exam, really what you're trying to do, it's an opportunity for you to demonstrate your understanding. And I know that even if you have a bad day, you understand more than nothing, right? So help me to give you points on the exam, right? Write stuff down, right? Even if it's just this, where you write down the first law, right? And then you make these assumptions and it gets delta U is equal to Q minus W. And then even if you don't know what the expression for work is, write down that you know that work is the integral of P dV. Oh, sorry, Dr. Schertz, I can't figure out what the pressure relationship is. But I know that it's this, right? And then even, I mean, if you really get stuck and you really can't do anything, make up a pressure volume relationship. Show me that you know how to do something, right? Same thing here, right? So here you're going to want to demonstrate that you can say, oh, it's water, and I can figure out what the phase is, and then I can put it in, right? Hopefully you just get it right. But if you don't get it right, at least make some kind of assumptions, right? Show that you can sort of work the problems instead of just getting to a dead end, right? So do everything you can to not have a blank submission, right? Even if it's not perfect, right? It's better to have something than nothing, right? Because I can't try to get a handle on what you understand if you don't give me anything, right? Now, our other option, if it's not water, and this is the problem that we're going to do today, right? Because it's certainly a thing that you could see on an exam, right? And remember, there's two long answer problems, right? And there's two different kind of fluids that we can use. And there's two different measurement systems, right? So you might be able to kind of make some, intelligent guesses about what kind of systems you might see on the exam, right? So if it's an ideal gas, we'll either assume that it's constant specific heat, so that it's CV times delta T. Remember that because it's delta U, we need to use CV times delta T. Or if it's variable specific heat problem, then what we want to do is we want to use table A22. This is more accurate, but it takes longer because you have to interpolate on that table, right? Or if it's imperial units, like the problem we're going to do today, then you'll use, I think it's A22E and not AE22. But there's an E in there somewhere for the English, right? And then after you do all that, right? After you figure out this is the stuff that takes all the time, right? You got to fix all the states, right? How do you do this, right? How do you find this integral of PdV, right? Then you can find Q, right? Now, if you're somebody, so this happens to lots of people, right? Especially in this first exam, a lot of people struggle with the time, right? First, I mean, I guess that there's time pressure, right? So that always makes things a little bit harder if you're racing against the clock. So sometimes I encourage people to time themselves when they're doing their homework, just so that they're used to having the sort of like ticking clock in the background, right? And even if you don't really care what the time says, right? You just know it's another variable, right? The other thing that I would suggest is do as much as you can symbolically, because it probably takes 5 minutes, maybe 10 minutes to go through and get the full symbolic solution, right? And if you do that, you've demonstrated your understanding, right? But depending on what kind of interpolation you have, or if you're making mistakes or something, I mean, it could take you 20 minutes just to fix all the states, especially if you make a mistake and then you have to go back. And if all you did was fix the states, you didn't really demonstrate that you knew how to solve the problem, right? But if you do all the symbolic solution, you know, sometimes people talk about the Pareto's principle, right? Or sometimes the 80-20 principle, where, you know, you get 80% of the benefit from doing 20% of the work. Now, it doesn't necessarily correlate to your grade, right? But I think you get the bulk of the benefit. You demonstrate the bulk of your understanding by doing the symbolic solution, which doesn't take all that much time. So my encouragement is to get you to solve the whole problem symbolically, right? And we'll do that for the problem here. We'll do everything symbolically first, at least as much as we can. And then I'll show you that, because we'll do it both ways. We'll do it as CV delta T and using table A22. But it ultimately doesn't matter. That's just, you know, it's like the topping on top of a sundae or something. I don't know. It's probably a terrible analogy, right? But it's like, it doesn't really matter, right? It's, you know, it's not the meat of the problem, right? So then the last thing you do is you say, does it make sense? Oftentimes we'll have just a bonus question at the end, right? It's not really bonus because it's part of your grade, right? But it says, you know, comment on the sign of the heat transfer. Even if you don't have a number here, you write down in the box, heat in is positive, heat out is negative. So if I had a positive number, then I know heat is going in. And if I had a negative number, then I know heat is going out. Because then who cares what your answer is for that, you know, part E of the problem or whatever? Really what I'm asking you is, what's the sign convention for heat? And what's the sign convention for work? So even if you can't get a number, you just write that down. And I'm like, oh, right? Mike knows what he's doing, right? So so then I was talking about me. Sorry, Michael. I know you know what you're doing too. Right? Right? But then it shows, it demonstrates that you understand what's going on with the sign conventions, right? So, you know, ideally you're going to get everything perfect, right? In the real world, you might not have a perfect solution, but there's things you can do to demonstrate your understanding that don't necessarily take a lot of effort or time. And I think that's really important when you're writing exams, right? So what are those pinch points, right? What are the things where you get sort of an outsized benefit for the amount of effort that you put in? All right, so today we're going to go through this problem. So this is a problem. I don't think we've done a first law problem yet on ideal gases. And I don't think we've done a first law problem yet in class that uses imperial measurements. So we're going to do both today, right? So this, we have an ideal gas problem. We know that we start here at state 1 at 80 psi and 0.1, that should be cubic feet because it's volume, right? So a higher pressure, a smaller volume, right? And we know the mass is 0.01 pounds of air, pounds mass, right? Now, remember from the early, you know, videos that I asked you to watch by yourself, you know, which that's testable material because it can be in the multiple choice problems, right? Pounds mass and pounds force, even though they have the same first word, they're two different things, two different units, right? Right, state 2, we know that the pressure drops, and we know that PV to the 1.5 is constant. Now, this problem is nice to us. It tells us here what the specific gas constant is, right? Because this is R and not R bar. If you get a problem on the exam and it only tells you R bar, right? That's going to be the way you can tell, right? Is the specific gas constant we're looking for, whether it's in metric or imperial, is going to talk about the unit of stuff that we have in terms of mass. So it'll be pounds mass like it is here, or it'll be kilograms if it's metric, right? But if it's R bar, it'll talk about pound mole, right? Or it'll talk about moles, right? That's like Avogadro's number of atoms or molecules, right? So That's the way that we can tell the difference between R and R bar. I might give you both on a long answer problem. I'll give you R and R bar, and that gives you the opportunity to demonstrate that you know which value you're supposed to use when you're using the ideal gas law. We're asked to find the work performed by the system and the heat transferred to the system, right? So now, because this says by the system and to the system, we might think that it's sort of giving us a hint about what the sign is here, but I wouldn't necessarily believe that to be true. This is just, these words are chosen just because it's the sign convention. But basically, no matter what it says, I would write down what my own sign convention is. I'm going to say the work in is positive and heat in is negative, right? Or the other way around. Heat in is positive and work in is negative, right? Hip to win, right? And we're going to do this problem first, well, once by assuming that the specific heat is constant, and once by assuming that the specific heat is negative. Because as we get to these internal gas or these ideal gas problems, there's two different ways we can go, and I want to show you how we do it either way. Okay, so now I'm going to pull up. This is just the same problem. So, assumptions, right? So we always want to start with assumptions. Sometimes on an exam, this will be its own section, and sometimes it won't be. Sometimes it'll just say in the problem statement, write down your assumptions as you make them, right? That's kind of how I think about it, you know, because, you know, I'm making the assumptions because they help me use the equations. I'm not just making them to make them, you know. So my first assumption is going to be that it's a closed system, right? And what that does for me, right, it opens up the idea that I can use this equation, E2 minus E1 is equal to Q minus W. Right, so this is my first assumption. My second and third assumptions are going to be that the change in the kinetic energy is equal to the change in the potential energy, which is equal to 0. And because I made that assumption, right, this is going to become U2 minus U1, which is the same thing as the mass times U2 minus U1, and that's going to be equal to Q minus W. This is a really common place to get to, right? And like I said, almost, I mean, maybe you might get a problem where you don't make these assumptions, but this path is a path that you can take at the beginning of almost every problem, right? Maybe you have to write in, you know, 1/2 mv squared or something over here, right? But basically you can do this for every problem, right? Now, we know that the things that we'll need to do, right, we want to find, right, this problem asks us to find the heat transfer and the work, right? We know that the work is going to be the integral from V1 to V2 of P dV. I think we're given the mass, right? It was like 0.01 pounds or something like that, right? So this we're given. What we want to be able to do is find U2 and U1. And in order to do that, we need to be able to say, what's the fluid? Right? In this case, it's air, which is an ideal gas. And then there's two different ways that we can do this. And we're going to do it both ways. We can say assumption 4 is constant specific heat, right? And then under this assumption, delta U will become CV times delta T, and we'll never even find the individual specific internal energies, right? The other option, which isn't really an assumption, is variable specific heat. And if that's the case, we'll use table A22E in this case because it's imperial units, right? So just there in whatever that 3 minutes were or something, I've at least I've sketched out the scaffold for me to solve this problem, right? I don't have the answers yet or anything, but I got a roadmap, right? And I got some choices I can make. I can either go after the work first, or I can try to solve the specific internal energy first, right? Now, even before this, and again, you might have problems that give you a state table like this, or you might have to make it yourself. But this is my state table, right? I got temperature. This is in degrees Rankine. Whenever I have an ideal gas problem, I want to convert the temperatures to either Kelvin or Rankine, because here I've got to use equations like the ideal gas law. PV is equal to RT, right? Or MRT, depending on a big V or a little v, right? But that T is not a delta T, right? Which means that it has to be an absolute temperature, right? And if I'm using table A22E, right, then here on the table, I got variable specific heat. I got one of the columns there is in absolute temperature, whether it's Rankine or Kelvin. But I don't know any of the temperatures, at least not yet, right? I do know the pressures. I start off at 80 psi and I get down to atmospheric pressure, which is 14.7 pounds per square inch. Here I wrote psi, but it might be useful for me to remember that this is pounds force per inches squared. This volume is cubic feet and not square feet, right? And then my values for specific internal energy will be in BTU per pound mass. One second, I just want to make sure I've got the solution open, so if I need to find some numbers, I can do that. Okay, so what do we know? We know that our answer, at least right now, looks like the mass times U2 minus U1 is equal to Q from 1 to 2 minus W from 1 to 2. We know the mass, but I always like to stop and take account of what we know and what we don't know. At this point, it doesn't look all that pretty. It's good we got an equation, right? The bad news is we don't really know anything, right? So I'm going to start, because I know eventually I'm going to have to make a choice here for what's the fluid, but I'm going to do the stuff that I don't have to make a choice first. So here I'm going to, we know that this is going to be last, right? Because the heat transfer wasn't given to us. So we got to figure out everything else, and we'll use the first law to find the heat transfer. The first thing I'm going to do is find the work, right? So here I know that work is equal to the integral from state 1 to state 2 of P dV. I also know that the problem told me over here that PV to the 1.5 was equal to some constant, right? And that means that P is equal to some constant, V to the negative 1.5. All right, so I'm going to put that back in over here. Now, if you just remember what the answer is going to be, that's fine. But I'm going to go through the actual calculus here, right? So this is going to be the integral from state 1 to state 2 of CV to the negative 1.5 dV.
Professor, on the exam, do you want us to go through the integral, or can we just skip to the...
You can skip to the end if you like.
Okay.
Just make sure you get it right.
Okay.
Right? So it's a question of, for some, right, what you're trying to do is demonstrate your understanding. So I would say as long as you write this down and then write the answer down, that's okay. Because then you're showing me that you know where it comes from. But if you get it wrong, then it's probably going to hurt you a little bit. But if you got it wrong doing the integral, it would hurt you too. Right, so this, we're going to, the C comes out, right? We integrate V to the negative 1.5 dV, right, from 1 to 2. This is going to become C over negative 0.5 V to the negative 0.5 from 1 to 2, or I can just say 2 minus V1 to the negative 0.5. Now this is the tricky part, right? Because here we have to remember that C is equal to V2, right? Because C is equal to P2 V2 to the 1.5, but it's also equal to P1 V1 to the 1.5. So over here, I'm going to multiply by this version of C, and over here, I'm going to multiply by this version of C, right? And what I'm going to get is that 1 over negative 0.5 is equal to, right, P2 V2 to the 1.5 times V2 to the negative 1.5 is just going to be P2 V2 minus, same thing over here, P1 V1. You can leave it like this. I think it's a little cleaner if I say 1 over 0.5. So I'm multiplying everything by negative 1. P1 V1 minus P2 V2, right? It's also true, right? So if you get pressure is constant, or if you get that volume is constant, or if you get that PV is a linear relationship, I would write this down, but then I could also say it's also the area under a PV curve, right? So this I would particularly do if P was constant, right? Then this is a rectangle. If V is constant, this is just 0. Oops. So if V is constant, right, this is just 0. And if, I guess I should put commas or colons or something here. And if linear, right, then this is a triangle plus a rectangle. So sometimes it's better to actually do the calculus, right, or to just remember that this is going to be the result. But other times it's better to just remember this is the area under a PV curve, and you can get to the answer faster using geometry. So remember, the reason that we're doing this is that we don't know the work, right? So what do we know over here, right? Let's go back to our state table. We do know P1 and V1. We know P2, but we don't know V2. So here, right, we know P1 and V1. We know P2, but we don't know V2. So what I would do here, right, is I'm going to try to use, I could use the ideal gas law, potentially at state 2. So my options, I could try to use the ideal gas law at state 2, right, because this is PV is equal to MRT, right, all at state 2. But the problem is I don't know temperature at state 2 and I don't know volume at state 2, so I can't do this, right? But I do know that P1 V1 to the 1.5 is equal to a constant, which is equal to P2 V2 to the 1.5. So I can rearrange this. In this expression, I know P1 and V1 and P2. The only thing I don't know here is V2. So the way that I'm going to do this to try to save myself some headache from units is I'm going to write this as V2 to the 1.5. That's what I'm trying to isolate, is going to be equal to V1 to the 1.5 multiplied by a ratio of the pressures. So as long as the pressures are in the same units, we're okay. This is going to be P1 over P2. So if I start to put numbers in, well, I guess I could then take this guy here, right, and move it over here. So all this becomes 1 over 1.5, right? So now what I can do, right, so now the units here, this is going to be in PSI. This is going to be in PSI. So the cool thing here is that this pressure term is just a ratio of pressures. It has no dimensions, right? This is going to be cubic feet to the 1.5 multiplied by 1 over 1.5. So that's going to cancel, and this is just going to become cubic feet, right? So that's using an expression like this and setting it up as P over P, instead of trying to find the value of C first. C is going to have some kind of weird units, right? So then I'm just going to use that to find the volume, right? And in this case, V2 is 0.3 cubic feet. I'm going to put that back up here. And this fits with our understanding, right? Because the pressure is coming down. That must mean that because we're not losing any mass, so it means that it makes sense that the volume is getting bigger. Right, so that's good. So now I know this pressure, and because I know the pressure, or because I know the volume, right, now I know this work, right? So now this is going to be, when I put this into units, I won't do all the math, but I'll show you the units here. This is going to be pounds force per inches squared multiplied by cubic feet, right? Now, this is no fun, right? This is why nobody likes imperial units in this class, because this unit doesn't make any sense, right? We want some kind of force times some kind of a distance here, right? Which then we'll have to change to BTU. So first thing what I want is I want something like foot-pounds, right? So I'm going to, this is inches squared, I'm sorry. So I'm going to try to get rid of inches on the bottom, right? So here I know that there are 12 inches per 1 foot, right? But I got square inches, right? So that's going to get rid of this. This square feet is going to get rid of 2 of these feet, and I'm going to have pounds force, right? So now I'm going to have pounds force times feet, which is good. That's foot-pounds, right? So this is energy, which is good because we want to have energy because it's work. Work should be in units of energy. But when I look up U on the table, it's going to be in BTU per pound mass. So here, if you haven't already, you can go to the tab on my courses called Online Exam Materials. And that online exam materials will tell you the conversion to from foot-pounds to BTU, right? So here, I don't have what the right number is here.
I think it's 778 foot-pounds per. Yeah.
Yeah, that sounds good, right? So I think that when we multiply this, what I got was 1,034 foot-pounds force, or foot-pounds, right? But now I want to divide by 778 foot-pounds per BTU. And then this is going to divide over here. And this is now in the denominator 1 over BTU, so that'll flip up. So this will be like 1.3 or something like that, right? So especially anytime you get a problem that's in these English units, you know, your spidey senses start tingling, the hairs on the back of your neck should stand up. Units are going to be a problem, right? So it's tough in metric too, but certainly when you start to get problems in imperial, this is a big deal. So now we've got work, right? Work went from being an unknown to now a known, right? That's great. Now what we want to find is this delta U, right? So we can start here by first, we know what's the fluid. It's an ideal gas. Now, option 1, we're going to say constant specific heat. This one's nice because it takes less time, right? So this instead, so every time we have change in specific internal energy, this is going to be replaced with CV times delta T, right? So we're never going to find the individual specific internal energies, which is okay because the first law only asks us for the change. But in order to do this, you have to write down that you're assuming constant specific heat, because otherwise you can't use this expression. So now my expression is going to be mass times CV times T2 minus T1 is equal to Q minus W. This I can look up. I think that this is in table, maybe it's A20-ish, right? They have specific heat values for different ideal gases, right? Now we know work, we don't know the heat transfer, and unfortunately we don't know either of the two temperatures. So here's what we can do, right? We remember that this fluid is an ideal gas. If you have a fluid that's an ideal gas, again, in the back of your mind, you got to remember, you might have to use the ideal gas law, right? So the ideal gas law tells you PV is equal to mRT, or that P times little v is equal to R and T. Now in this problem, because we know the volumes, I'm going to cross that one out and we'll go ahead with this one, right? So I prefer not to use this version of the equation if I can help it. But I have to use it at least once because there's no state that I know everything about. Right? So here what I'm going to say is T1, I'm going to isolate for T1 here, is going to be P1 V1 over MR. Right? So this was what? This was 80 pound force per inches squared times the volume was 0.1 cubic feet. The mass was, I think, 0.01 pound mass, right? And then R was going to be, what did it tell us R was? Here, I got the... R is 53.35. Now we'll hope the units work out, but remember the units I always got to be on guard for. So this is going to be foot pounds force per pound mass degree Rankine. So what's going to happen to my units here? My pounds mass are going to cancel out. That's good because otherwise I don't have those. I want the Rankine to stick around because I want to get an answer in temperature, right? So here I got that problem again where I can say 12 squared feet squared per, inches squared per foot squared. The inches will cancel. This will cancel. This is going to be foot pounds. Foot pounds cancels over here. So it looks like after I do this conversion, right, to get rid of the square inches, then everything else works out and I get an answer of, I think it's 866. And then my units are 1 over Rankine. So my units, so 8, what did I say, 866?
Yes, you did.
866. My units here are 1 over Rankine, which is just 866 degrees Rankine. So this is good. I know T1. But this way is a little harder because I had to do all of the points, right? So what I'm going to do instead for the next state is I'm going to notice that it's also still from the ideal gas law. So PV over MR, PV over T is equal to MR. Now what I know is that the mass is constant. And because there's no chemical reactions happening, R, so the gas is not changing chemical composition, R is also constant. So that means that P1 V1 over T1 is equal to P2 V2 over T2. So now I can do something similar to what I did before. I can rearrange this, isolate for T2, say that T2 is equal to T1 multiplied by P2 over P1. As long as my pressures are in the same units, this is fine. I don't have to worry about the unit conversions. And then I'm going to get V2 over V1. Again, as long as these units are the same, right? And here I get that this is equal to 477 Rankine. And so far, even though I wrote down that I am assuming constant specific heat, I haven't actually used the expression for constant specific heat yet. This is all just ideal gas law stuff. And I've defined the temperatures. So now I know T1 and T2. So the only thing I don't know here in this equation is Q. So I can figure out Q for this equation. And I get that this is equal to 517. It looks like I changed this. This is foot pounds force, right? But then if I wanted to, I can take this in 778 foot pounds per BTU. And I can get an answer in BTU, right? So a little bit less than 1. So that's with constant specific heat. But what if I wanted to use variable specific heat as well, right? So the good news is if I'm using variable specific heat, I still go through the same process to fix the temperatures. I can still use the ideal gas law to find T1 and T2. But if it's variable specific heat, now what I need to do is I know that my temperatures are 866 and 477. So I got to integrate or interpolate in here and find the values of U. Right, so this is for state 1 and state 2. Right, now interpolation is something that we, hopefully you feel comfortable doing that already. The numbers that I got were for state 1, I got 148.6 BTU per pound mass, right? And over here, I got 82. Oh, this has got to be wrong, right? So it looks like I made a mistake here because my number was 82.37. So, right, I know I have to be between 78 and 81. So it looks like I made some kind of a clerical error here. So this number is not correct. But you would interpolate, we're what did we say? 477. So if I was on an exam and going really quickly, or if I did this and got a number that was wrong, instead of doing the interpolation again, I would say, oh, Professor Schertzer, 477 is approximately equal to 480. So I'm just going to take H2 or U2 as being 81.77 BTU per pound mass. Right? And now I'm going to put this, remember, because now it's variable specific heat. So, Sebastian, did you have a question?
Yeah. How do you know, like how you just did, you just said 477 is close to 480. So like what would be like a threshold that
this
is
always
like
a good question. In this case, the class ends in 2 minutes, so my threshold is let's get an answer, right? But here, right, so this is it's a range of 20, and we're talking about 3 degrees. So 3 on 20 is like, what, 15%? So that's a pretty big range. It's not ideal, but in real life, you would just want to know what your application is and how much uncertainty you can sort of deal with, right? Versus how much time you have to find it, right? Because it's always a trade-off as an engineer. To get a more accurate answer is going to cost more time and more money. So what we want to know is in our application, what's the most amount of uncertainty that we can tolerate and still deliver the outcome that we want.
okay, and if we just say this on a test, you'll be okay with that?
Probably, but you want to say what you're doing, right? I'm less concerned with exactly the numbers. And as we go deeper in the exams, this exam, you are sort of being tested on how to interpolate, right? But as we move further, like exam 2, I'm more comfortable with you not interpolating. Exam 3, I'm even more comfortable with you not interpolating. So you do want to demonstrate that you know how to interpolate. That is one of the skills we're testing on the first exam. But, I mean, you know, if you make a reasonable case, I don't think that you'll be hurt. I'm more interested in, can you do the first law? But I wouldn't just skip it entirely. You'd want to show somewhere in your solution that you know how to interpolate. Now my first law was the mass times U2 minus U1 is equal to Q minus W. And I know everything in this expression now, except Q. So here I can use this to solve for Q. Right now, the number that I got here was looked like 0.66 BTU. But I know that there's an error in that solution, but it's probably pretty close. So it's probably something like this, right? So this is a positive number. That means heat is going in. My work, right, because my volume was increasing, the work that I got was also positive, right? So that means that work was going out because the thing was expanding. So work was also positive. And I think that that was everything that they asked us to do in this problem. Did you have questions? I know we're a little bit over, but or we're maybe right at the buzzer here, but I'm happy to stick around for questions. And I'll give details on sort of the exam either next class or Friday. I'm still working on scheduling it.
Thank you, Professor.
Have a good afternoon.
Yep, you too.
Thank you, Professor. Have a good afternoon.
No problem, you too.